We all, this is Darrell Berry Jr., back doing some linear algebra, preparing for a project that is due uh, tomorrow. So I'm looking at one of the first problems I'm doing is about inconsistent systems, basically a system of equations that does not have a solution and how we solve those ironically. So I plan to go ahead and go through this first section. I'll see if I can, let me see what's happening with my book here. Oh, hold up. Let's see. I got you. All right. So we'll go ahead and see what's going on with the process in this chapter 4, section 1, and see about solving some of these problems that we have here. So I changed my setup a little bit. I'll have my full pad here and my full book here and go back and forth, and we'll see how this goes. So looking at chapter 4, we have projections and linear transformations. An inconsistent linear system, AX equals B, has, of course, no solution. It's ironic. So we're solving systems that don't have a solution to speak of. And I'll adjust my volume just a little bit and see if I can make sure it's not too loud. And let me know in the chat if anybody joins if my volume needs any more adjustment. So inconsistent system. So this is our system, AX equals B, but it has no solution. So a consistent system has one plus solution. We might try to do the best we can by solving instead the system AX equals P. So basically what we're going to do is solve a similar system. So it seems like an approximation, just like how a Taylor expansion. Like I remember for my galaxies and cosmology class, we had to do this complex calculation, an integral of this complex exponential, and there was some kind of fancy, I don't even remember the word of it, but some kind of function that simplifies it. I don't even remember what the name of the function is, but suffice it to say, I could do a Taylor expansion. So I did a Taylor expansion up to 5 degrees, which made it pretty approximate, and I got an answer very, very close to the actual answer. I was like within hundredths of a point or something like that. So it seems like something like this is similar. Basically, what we're going to do is basically get some kind of approximation to the answer and go with that. So we'll see how that goes. Where P is the vector closest to B, lying in the column space of A, right? This naturally involves the notation of projection of vectors and Rn onto subspaces, which is our fundamental example of linear transformation. In this chapter, we continue the discussion initiated in chapter 2 of linear transformations, the functions underlying matrices. So linear transformations underlie matrices. We will see that a given linear transformation can be represented by quite different matrices, depending on the underlying basis or coordinate system for our vector space. So the same different matrices can do the same thing. Our perpetuous choice of basis can lead to a more convenient matrix representation and a better understanding of the linear transformation itself, giving or indicating a good chance of success. All right? Inconsistent systems. That was just chapter 4 intro. right? So we have that. So suppose we're given the system ax equals b to solve, where a equals 2, 1, 0, 1, and 1, 1, 1, 1, and b equals 2, 1, 1, negative 1. As the reader can check, b is not in a column space of A. Right, so I'm actually unclear about the column space thing, so I'll go back to that. What I may need to do is make a video just about column spaces, because right. But let's see if this process can help elucidate column spaces, and then we can go back to that. As the reader can check, B is not in the column space of A, therefore inconsistent. So in order to be consistent, it needs to be in the column space. Right. So instead, we're going to solve AX equals P, where P is in the column space of A. Both is B. So that seems very important to have that in bold. All right. So they give us a lemma 1.1 about this principle. Suppose V is in Rm, is a subspace, and B is in Rm, and P is in V, such that V minus P is in the transpose, or actually is orthogonal to V. So that would tell me that we have our vector space, and this line would be B minus P. So you can say that one of these is going to be B, and one of these is going to be P. So I'll just say that this is B, and this is P. P is in the column space. B is not, but they're close. This might be a bad drawing, but it's the idea of how I think about it. Thus, the magnitude of B minus P is less than the magnitude of B minus Q for all other Q that's in V. So it's shorter. It's the closest. So we can say that this would be, I'm not sure how to draw it, but I'm sure we'll see. Oh, ain't that something? We have a similar drawing right on the next page. So I guess I wasn't that far off. So I have, oh, well, that's pretty good. So some adjustments here. We have B going there, P is going there. This will actually be my triangle. The right triangle. Uh, this is P. Going this way. And looks like I need to make it at a slight angle. So this would be P. This would be Q. And I'm actually make them longer. This would be P. This would be Q. And B is not in the column space, is not in the plane. P is. So P can be solved. Right? And I was correct that this is the space. So since B minus P is perpendicular to V, evidenced by this perpendicular line here to the red line, B minus P, perpendicular to the plane, and Q minus P is in the space. So this is Q minus P right here. Q minus P is in this space. Right? So B minus P is perpendicular. Q minus P is in the space. So that means that B minus P dot Q minus P equals 0, and thus they're orthogonal and form a right triangle with the hypotenuse. Right. B minus Q is the hypotenuse. So maybe I understand this a bit better than I thought, kind of intuitively. But I do still need to get the uh you know sort of more but technical mathematical writing down for the column space and all that stuff, because I know I got that incorrect on the exam, but I focused on the other stuff that I frankly enjoyed doing more. I need to learn other stuff too, right? So we'll call this figure 1.1 like the book. Thus, by the Pythagorean theorem, the magnitude of b minus q is greater than the magnitude of b minus p, obviously. So p is closer to b than every other point. Okay, that makes sense. So basically, we're just making getting the orthogonal line to the space to B, which gives us the closest point from the space to B. And P ends at that point. So we have to remember that B is a vector, as well as at a certain point in space relative to that plane. And you drop a vertical line from B to the plane, draw a line from where B intersects the base of B, intersects the plane to the right angle point, and thus you get P, and that's what we're going to solve for. So I see the logic behind it. So P is closest to B. Right? So that makes sense. And if anybody pops up, you guys in the live chat, or if you have any questions, comments, put them in the comments to the video. Also, be sure to join my Discord. We can talk all things science and math, astronomy, and computer science, and I can use help with that there. All right. So it says, recall theorem 4.9 of chapter 3. Any subspace V in Rm and V in Rm, there is a unique V equals P plus B minus P, where P is in this space and B minus P is orthogonal to the space, right? B equals P plus B minus P. Makes sense. Now let me actually draw this to make this more clear. We have B here. We have P. And we have B minus P. Thus, B equals P plus B minus P equals P plus B minus P equals B. So that's a true statement. This leads to the following definition. Definition. Let V be a subspace of Rm and B be in Rm the projection of B onto V is uniquely P, which is in V, given that V minus P is orthogonal to the space. Therefore, P equals the projection onto the space V of B. And I love the projection process. Understand that well. So we're talking about language here. And it gives a remark since the orthogonal to V, the orthogonal to that is V. This follows that the projection of was orthogonal to V onto B, so the projection of this onto B the projection of what's orthogonal to V onto B equals B minus P. So whatever is orthogonal is whatever is going in this direction. I project it onto B, yes, I will get just that length. Or I see, I had it backwards. The projection of B onto what's orthogonal is that. I was saying it wrong. I was thinking, hold up, wouldn't it be sideways like that? But this thing is always written kind of weird. So what is the big letter is what's being projected. So B is being projected. And what's down here was being projected on the orthogonal. So B is being projected onto this and becomes that. B minus P. So that equals B minus projection of B onto V. All right, that makes sense. So if I project B on into V, I get this. P. So that's this right here. And if I project B onto the orthogonal to V, I get this, the orthogonal to V. So everything is adding up. Note that B minus P is in the orthogonal, and B minus P is P, which is in the orthogonal to the orthogonal. So now that it's doing too much. All right, well, maybe not. This next line is okay. P is orthogonal to the orthogonal. Could have just said that. P is in the orthogonal to the orthogonal. So B equals the projection onto V of B plus the projection onto V orthogonal of B, which makes sense. So the projection of B onto V is this. Projection of B onto V, and the projection of B onto the orthogonal to V is this. So that makes sense. So now we have V in terms of two projections. So this book is mostly, overall, I mean, it does a good job of just plain wording, but I do believe this could have been worded better by simply adding the fact that uh, this could have just been, those not put in right there, but it's not a big deal. To calculate P explicitly, we proceed as follows. So I think I'm at a point where I can calculate P, but I'm not sure though. So let's keep going. To calculate P explicitly, we shall proceed as follows. So we'll say calculating P. So V is an Rn, span is V1, V2, Vn is a basis for V because it spans V. And A is M by N, and columns are V1, V2, Vn. And we want to solve AX, I'm not sure what the bar means, equals P, where V minus P is in the column space of A orthogonal. Is orthogonal to the column space of A. Well, theorem 2.5 of chapter 3, by theorem 2.5 of chapter 3, column space orthogonal to column space of A equals, I guess I do remember this vaguely. So now we can rewrite our problem as a pair of equations. We want to bring this down and say AX equals P, and A transpose B minus P equals 0. And this was the column space. Okay, so let's think about this. So what I'm saying is B minus P is in the column space of A orthogonal. And if I multiply this by a transpose, orthogonal transpose. It's the only thing I can see, but I don't think that's it. So I have to figure out how they got to this line right here. This line right here, how did they get this? Right. And it says, so this is 1, this is 2. So sub 1 into 2 gives A transpose A, that's the B minus P that gets us close equals A T skip the line. B minus A D line equals 0. Now we have A T B minus A T A X equals 0. Thus A T A X equals A T B. We already know this equation has at least a solution because P exists. Since by construction, the rank of A is n, we claim that AT A is non-singular. Since by construction, rank of A equals n, A transpose A is non-singular, and it says suppose X is n A transpose A, right? So I'll go ahead and stop here, and what I'll do is come back later and do some column space stuff. I'll just make sure that I get the column space stuff down, and we'll start from here with the column space, null space, column space, orthogonal, the transpose, and so on and so forth. We'll see if we can understand this a bit better, but I can forge on to the problem, but I'll develop a greater understanding. So I'll come back either or later today. I'll probably take a break and do some physics stuff. I have a lab I'm doing. What am I doing now? I'm basically establishing that relativity is a thing by using Compton scattering and the Compton edge. So got all my graphs going along pretty good. Now I just have to figure out the Compton edge. So I'm working on that. And eventually what I'm going to do is I'm going to make some talks or presentations on some of my labs this semester. Well, maybe all of my labs. They're all pretty fun so far. As long as they, are doing decently well. They did good on my speed of light one. I'm waiting on my grade for my quantum, establishing that quantum exists, uh, with exciting some gases and with some voltages and noticing the discrete drop in the energy when the electron reaches a certain amount of electron volts because of being accelerated by the voltage. I see that transferred into the atoms of the gases, and now we're doing some relativity validation. So all three of these will make some good presentations. So look forward to that in the future, and look forward to me later today. We'll do some column space and vector space like that. So see y'all later.